Hi everybody, my name is Stefano Doni and welcome to my session on Java performance in 2021, how AI optimization will debunk for long-standing Java tuning myth. A quick intro about myself. I'm very passionate about performance optimization. I actually started doing capacity planning and performance work 16 years ago. I'm a co-founder and CTO at Akamas, where we do a new breed of software using AI for performance optimization. So let's get started. Firstly, I want to introduce Java performance tuning and why it is important. Then we are going to see how people do performance tuning today and where does AI fit into the performance tuning process. So when we talk about Java performance, one of the areas that is definitely hot these days is tuning the Java virtual machine, which is the engine that actually runs our Java applications. Java is a very popular platform and lots of material has been published over the years on how to tune the parameters of a JVM to extract more performance or reduce the infrastructure cost of running Java applications. But as you are going to see in this presentation, the benefits of JVM tuning can be very significant. Double digits improvements are typical. But besides performance, JVM tuning is also important to ensure service reliability. As you can see in this example, JVM tuning significantly impart the ability of a Java service to sustain peak traffic levels without service disruptions, while the default configuration actually slowed down under peak load and then crashed. So I'd like to quote this great book here by Scott Oates from Oracle. It's a fantastic resource that I definitely recommend this book if you want to learn more about how to tune the JVMs and the inner workings. It's nice to see that Oracle itself recommending that the JVM tuning is an essential activity. If you are not into JVM tuning, it may be surprising to know that the JVM is an extraordinary piece of software and it's also highly configurable. It literally has hundreds of options that we as performance engineers can tune to achieve optimal performance of our applications. If you're wondering about how many options a modern JVM actually has, here you can see the actual number for the different JDK releases. Java 11 is the current most widely used JDK, and it has more than 800 total configuration options, of which I would say more than 100 can have a pretty significant performance impact. So we have seen that JVM tuning is an essential process, but the JVM itself is a very complex machine. So how does JVM tuning get done today? It's typically an iterative and trial and error process where we test the performance of our app, we analyze the result, and we see if it improved or not. Then we decide to change some VM options based on the analysis of the performance, and then we repeat the process. To guide us in the tuning process, we rely on vendor best practices like the Java Performance book that gave us some fundamental models of performance that we need to keep in mind to reason about Java performance. For example, to assess if there is a need to tune the JVM garbage collector. The key point of this talk is to look at a couple of those Java tuning best practices or beliefs and see if they are actually true. To do that, let me first introduce the role of AI into the tuning process and how did we actually came to question the belief that we had always used. So where does AI fit into the tuning process? AI is changing entire industries, and there are many discussions about how AI can help the performance engineer being more productive and deliver more value. One way where AI can bring a lot of value is in making the performance tuning process much faster and more automated. In an AI-driven tuning process, AI can be used to navigate the hugely complex optimization space of a JVM options and identify the best configurations much more quickly. Not only that, the AI optimization process can really become goal-driven, where the goal could be a business or an application metric that we want to minimize or maximize, like the cost or maximize the transaction per second of our services. So now we are ready to start debunking our Java performance myth. So we at Akamas, we have used AI to optimize hundreds of Java applications, and we got some very unique and interesting evidence in this process. So let's get started and see what we as performance engineers can learn by looking at the result AI was able to achieve. So let's start with the first myth. If you are into JVM tuning, you know that the main target of tuning is actually the garbage collector. So the GC is the process that JVM uses for memory management. a huge focus is put on making the GC run faster so that it won't impact the application performance. But are we really sure that this is the right thing to do? Let's look into more detail. So to let you understand this myth, let me quickly define some key garbage collection performance metrics. So in a nutshell, the main task of garbage collection is to free memory, but to do that, it has to stop application threads. The amount of time it stops the application threads is called GC pause, and the percentage of time spent doing GC is called the GC overhead or GC time. Throughput is the percentage of time the application threads actually run. So if we have 20% GC time, my throughput will be 80%. Last important property is footprint, which is how much memory or CPU the JVM actually requires to run. So here is the golden rule of Java garbage collection performance. You need to lower garbage collection time. If we think about it, it makes totally sense. If we decrease the garbage collection time, we will get higher throughput, meaning that the application threads can run for more time without being stopped. I took this chart from the official Oracle docs, and it clearly shows the significant impact of garbage collection time can have on application throughput and also scalability. It was created using the well-known Amdahl's law. So again, it makes totally sense to minimize the GC time. This performance rule is so ingrained in our industry that it is also the main best practice we use in JVM tuning activities, and it is even implemented by market-leading application performance monitoring tools as a key metric to suggest the need for JVM tuning. But as I'm going to show you that the GC overhead isn't everything, and it's not the only factor driving application performance. So what you can see here is the result of an AI-driven optimization where we had a Spark application running on OpenJDK 11, and the goal for AI for this optimization was to minimize the execution time of the Spark job. In the chart, every dot that you can see is basically an execution of the application with different JVM options. For each run, we recorded the execution time and the garbage collection overhead. The yellow dot is the baseline configuration, which is the JVM with default settings. You can see a couple of very interesting results here. First of all, the best configuration was about 30% faster than the baseline. So a pretty significant result that AI was able to achieve by tuning the JVM parameters. But look at what happens at the GC overhead. So the best configuration actually had the higher garbage collection overhead and almost 2x overhead actually with respect to the baseline configuration. So it's very interesting to observe the shape of this curve. We might have expected a kind of linear relationship. So the higher the garbage collection overhead, the higher the execution time. But instead we got this kind of a curve where the minimum execution time is achieved with about 30% garbage collection overhead. Please note that this level of overhead is pretty significant. Some application performance monitoring tools, for example, warn about a high overhead at about 15% garbage collection overhead. So it's not very low value here. So the key question for us as performance engineers is how can it be? How can the application run faster if the garbage collection is leaving less time for the application threads to run? There can be several ways in which garbage collection interacts with application performance and the underlying hardware that can explain what is happening here. Let's dig deeper. So to better understand what is happening here, we need to have a more in-depth look at what happens at the CPU level. So we used a tool to trace the CPU scheduler of the Linux operating system to see what was happening to the application and garbage collection threads that are scheduled by the Linux kernel into the actual processors. So this graph shows a visualization of how the different threads of the JVM are actually scheduled on the CPUs. There are many tools you can use to generate this chart. Linux Perf is an example. What you see here is Perfecto, which is a tool built by Google that is pretty new and runs entirely on your browser. So what the scheduler traces are telling us. So on the rows, you have the various JVM threads that we recorded. So the Spark application threads, you can see the Spark application threads on the top, the so-called executor task, and you can see the garbage collection threads on the bottom. Those are the JVM threads that actually perform garbage collection work. For each thread, you can see the running bar, which means that the thread is actually running on a CPU. So the first thing to notice is the GC pause in action. You can see the application threads are stopped and then they resume the execution after the garbage collection has completed. But if you look closely, you will notice that there are some garbage collection threads that are executed concurrently with the application threads. They are called G1 conc threads and they stand for concurrent threads. So this is a design feature of the OpenJDK 11 G1 GC, which use background threads to perform part of the collection process in order to reduce the stop the world pause. In the chart, each thread is marked as a dark green if it's running on the CPU and in light green if it's waiting to access the CPU. And here comes the explanation for the application slowdown. The garbage collection, the G1 GC concurrent threads are actually competing with the application threads to access the CPU. Hence, they are slowing down the application threads. Notice that these GC threads are not counted in GC overhead as they work concurrently with the application. So this is one of the reasons why looking at the GC overhead or GC time alone, it's not showing the full picture. So if you tune the JVMs to decrease the GC time, you may actually cause more harm than good, because you may actually asking the GC to do more concurrent work, which can actually slow down the application threads for much more time. So data tells me that this myth is actually busted. So the key takeaway here is that GC time is an important metric, but we need to keep in mind as performance engineers that simple GC overhead performance model might not work, as the JVMs and the hardware are complex machines, and sometimes they work in kind of unpredictable ways. When we tune, we should always consider the effect on the end-to-end application performance. So let's now move on to the second myth, which is another big classic. So this principle states that if we consider throughput, latency, and footprint, you can really have two of them. If you want a high throughput and low latency, for example, you will need a large infrastructure. You will have a large infrastructure footprint because the garbage collection will need more memory to make room for application allocations without stopping it too much. On the other side, if you want a low footprint and high throughput, you need to accept that you will have higher latency because the garbage collection will probably need to stop the application very often to keep with the application threads running as much as possible. So it looks like kind of law of physics that we cannot really escape. So let's see what we have found out. So this is another very surprising result that we got by tuning an enterprise application this time using AI, where the goal was to minimize the footprint, in particular the JVM heap size, the memory size of the JVM itself, while still maintaining the same level of performance. Let's look at what AI achieved. So in this case, the throughput of the application increased by 23%, and response time decreased by 22%, pretty much the same amount. So a pretty interesting result. But what is more striking is that the AI managed to make the application run faster, while at the same time it reduced the heap size by more than 80%. So the best JVM configuration actually improved the three key metrics here. So how can we explain a result like this one? So unfortunately, we couldn't get more low-level data on the environment in this case due to time constraints on the customer project, but nevertheless, we managed to repeat many times, both the baseline and the best configuration to make sure that the results were reproducible. So we also set up, after this project, some internal benchmark to study this effect, and we were able to reproduce it. So the key concept here is that if you look at the broader application performance picture, data shows that this myth is actually busted. I think that this principle is actually true if you look at the specific GC implementation. So you can really get latency, throughput, and low footprint at the same time when you design an algorithm like the garbage collector. But some way, this principle doesn't take into account what happens to the actual end-to-end system performance. If we consider the entire optimization space, we can find configuration that actually improve throughput, latency, and footprint at the same time. I think this is an important concept to remember. So let's go to the third myth. I often hear this myth. Should we still go and tune JVMs in 2021? Why don't we simply use the newer JVMs which offer constantly improved performance, newer low latency garbage collectors, and so on? Let's see what we learned here. So this one is interesting. So in our lab, we do a lot of performance testing and benchmarking to understand how JVM behave and how to better optimize them. This time we did a simple experiment with Renaissance, which is a popular open source Java benchmark. We ran the benchmark with the default configuration, again G1 GC here, with the increasing level of maximum heap from 2 to 5 gig. During the experiments, we measured some key metrics like the execution time, the garbage collection time, and also the max heap that was used during the experiment. So let's see what happened. So first of all, the execution time decreases as heap gets bigger. So this time something that we expect, so no surprises here. But look at the garbage collection overhead. So it increases with bigger heaps. This is interesting because when we see high garbage collection time, the first reaction we all have is to add more memory. More memory means that GC has more room to allow application allocation without needing to stop the application threads. But again, this example shows that the JVM might behave in ways that are not necessarily what we might predict with simple models, at least for this application. Most importantly, it's interesting to observe that they run with 5 gig. So in this case, G1 decided to use only 3.4 gig out of the 5 gig that were available. This is important because on one side, GC overhead is already pretty high, but G1 decided not to inflate the heap fully, even though it had an additional 1.6 gigabytes of memory available here. As you can see, G1 used some significant amount of CPU time also. It used 172 seconds out of the 223 seconds of the execution time. So this translates to almost 80% of one CPU being constantly used during GC. So what does that mean? So as you can see, G1 basically traded off CPU and overhead, which means throughput, to be more memory efficient. What if we wanted lower CPU footprint, or what if we wanted higher throughput? So in this case, G1 is prioritizing a different kind of goal here. I guess this example shows us an important concept that we need to keep in mind. So the JVM uses a complex set of heuristics to decide how to navigate the footprint and the latency trade-off. So such heuristics might not necessarily be aligned to our goals, but the good news is that we can tune them. So the JVMs are constantly improved and evolved, trying to be highly performant in every possible scenarios. However, the data that we have clearly shows that default behavior might be pretty far from optimal for the specific application and requirements that we have. So it's important to recognize that we have this optimization space and we can improve significantly the performance over the default values. So this is the last myth, and it's about cargo culting JVM configuration, which means basically copying and pasting JVM settings that work well for a given application scenario to different application scenarios. Here I want to mention two lessons that we learned by looking at some false myths that we encountered in our customer engagements. So the first one is related to GC thread tuning. So in particular, we find that people have various theories about how many threads a garbage collection should have of which type. An aspect that confuses many people is the difference between concurrent and parallel threads, which have very different role, as we have seen in the first myth. Parallel threads are used in the stop the work phases of garbage collection, so it makes sense to use all the available CPU power to make the pause shorter, while the concurrent GC threads can compete with the application threads, as we have seen. So depending on the application, they may have benefits increasing or decreasing them. This whole tuning may get a bit more tricky in container environments where there is no clear-cut definition of how many CPU the container actually have. So the JVM itself has some heuristics to auto-configure itself, but it's worth exploring this as well. The other kind of cargo cult we constantly see is setting initial heap equal to maximum heap. This is actually a high-performance best practice that is very commonly found. The problem here is that this best practice, as a matter of fact, turns off some strategies that JVMs use to manage memory in a more dynamic in a more elastic fashion, which can be important for cost reduction in container settings. So the JVM have always been considered a kind of memory hog on one side, but the reality is that, again, it comes down to the default settings. The default JVM behavior is actually geared more toward maximum performance. However, it can be configured to be memory efficient as well, even though you need to experiment with initial heap and other settings as they may impact the throughput of your application. So this could be a topic for another talk, but you can refer to the links for a greater explanation on how to optimize for memory efficiency. So again, I think this practice should be avoided, as different applications may run on different environments and have different performance goals. We see lots of developers doing copying and paste of configuration, and when you have lots of microservices, this can really have a bad impact on the overall application performance and infrastructure cost. So I guess this myth is also busted. So it's time to wrap up. So what did we learn in this talk? So JVM tuning is an essential topic today. So it's a hot topic, and rightly so. We have seen lots of examples of the significant benefits that JVM tuning can actually provide on application performance, reliability, and infrastructure cost. The bad news is that we debunked some of the performance best practices that we all use today to tune Java applications. So as performance engineers, this is a kind of bad news, as we rely on performance models and theories to drive our work. But we need to recognize that systems are becoming more and more complex, and too bad some simple performance model may no longer work. But there is actually hope. I really think that the future of performance engineering is bright, as we have new tools like AI that can help us be more productive and bring even more value if we are able to exploit the existing optimization potential that we have in our systems. So I hope you enjoyed the talk. Thanks a lot for your time, and let's get in touch if you have any feedback.
Thank you, Stefano. You are right. This was really interesting and controversial, because in a way you're telling performance engineers the robots are going to take you out of a job, right?
Well, it's a kind of a new approach, because actually I think the main concept is that it's becoming harder and harder actually. So I think that we need to recognize that. So we need to understand where we need to focus next. Yes.
But to be fair, when you talk about AI here, is it just a matter of brute forcing, or basically iterating through all the possible combinations and then choosing the optimum, which as a human being you'll give up when you have 350 different knobs to turn?
Yeah. In our product, basically we did a lot of research to actually use actual machine learning to explore this hugely complex optimization space and quickly understand where it's the optimal. So you cannot really do a kind of brute force, because there are literally billions of combinations. So it will take billions of years. So the fact that AI is much better suited for this task than the human brain, even for the expert brain, to be much quicker to understand where are the best region of the space, where are the space of this huge configuration space that it's not worth exploring. So it's really interesting on that regard.
And if you go back to Laurie's talk earlier in the day about benchmarks and how benchmarks can be misleading. So I think that adds another layer of complexity, because depending on the benchmark you use, say this is the right configuration, you might actually optimize for the wrong thing, because then the benchmark doesn't give you the predictable performance as he was mentioning, right?
Yeah.
Did you see that in your work?
Yeah, sure. Actually, what I've shown some examples that actually were driven from our internal benchmarks, but of course, what we do here is to use the actual customer application, the actual user application, to, of course, optimize for their own application, their own workload. It's true that we spend a lot of time in ensuring that our benchmarks actually are reproducible. So the whole topic of warm-up, it's something that we all struggle. We had problems also in the past on some particular Java benchmarking suites. about how to reach the actual stability of performance, because actually when you need to being able to understand if you are doing a 10% improvement due to the JVM settings, you need to be sure that this 10% is coming from exactly from the settings, and is not, for example, the noise of the operating system, the hardware, or even the JIT compiler that decide to, in a way, suddenly compile the code in a different way. So that was a great work, and something that we of course we need to improve it in general as an industry, I guess.
And I hear this. I think there will be a need of kind of constantly optimizing the JVM. So maybe even the whole job of I remember from my old days, the DB, special DB engineers that will come one day, they will run 1,000 scripts and will tell you, now your Oracle database is 10 times faster, and they would go. So this becomes more like, with this AI approach, will be like optimization as a service, right? Where you have something that kind of keeps monitoring your client's applications and keeps experimenting and slowly shifts the nodes depending on the workloads. Do you see a picture like that?
Yes, we are working on that direction. Yeah, on one side, we this relates also to the topic that Andy mentioned on Captain. So one side is integrating this kind of approach within the CI, so that you will be sure that you will be pushing to production, and not just in a way a code that is matching your SLA and of course the functional test, but also it will be optimized with respect to the configurations. But also the next step will be also tuning the system directly in productions. So based on real production workloads, etc. It's something that we are working on. Of course it's much more complex, but it's you will avoid all the benchmarking kind of problems.
Excellent, Stefano. Thank you so much. Looking forward for the conversation later.
Thanks a lot. Talk to you later.